Okay, everybody, back at it. This is going to be the second video that I'm doing here, and it is, as promised, Fundamental Theorem of Calculus, Part 2. So good stuff here, guys. So we're going to write down the Fundamental Theorem of Calculus, and if you want to go ahead and start that, you can. But let me talk about it real quick. So first of all, we've already gone over Part 1. That was the last video. Just said we can, that was just a connection that we can make. And that's why it's called the Fundamental Theorem of Calculus, guys. It's very important. It's telling us we can make a link between the two main concepts in calculus. Derivatives, antiderivatives, or derivatives and integrals. Okay. So the first half of this year, maybe more than the first half, I was focused on derivatives and applying them and knowing how to find derivatives, things like that. And this, from here on out, we're talking about integrals. So I mentioned earlier in this chapter when we were doing the Riemann sums, the left-hand, right-hand, and midpoint sums. I told you those were just approximations for finding areas under the curve. All right, I told you eventually we would get to the exact area. We'd be able to figure out the exact area of different functions. That's what we're going to get into today, finally. No, it's been a while. We had to go over a few properties and things like that. The Fundamental Theorem of Calculus Part 1. But now we're actually to that point. All right, we're actually going to find the exact area under the curve. And here is how. So let's go ahead. Let me scroll down here. So it says if f is continuous at every point of the interval a to b, and if capital F is any antiderivative. Remember, capital F means antiderivative. Okay, so if capital F is any antiderivative of little f on the interval from a to b, then what we can do is to find the integral from a to b of f of x dx. That is going to equal capital F of b minus capital F of a. All right, it's important to make sure you know that they're capital F's. So what you need to do is you need to find the antiderivative evaluated at b minus your antiderivative evaluated at a. So I'm hoping this video, guys, is going to be a little bit shorter than the last. I think I've only got 2 examples for you here. But I think if I show you these 2 examples, you can, you're good to go, I think. There's different functions that you could actually find the area under the curve, but I'm going to show you the process here in these 2 examples. All right, and they're going to be 2 different types of questions, so I want you to notice that as well. So if you need to pause this, you haven't got it written down, go ahead and do that. I'm going to move on here. So let's go ahead and before we get to that example, let's write this down first. Okay, sorry, I might have lied. I do that a lot. So in words, the Fundamental Theorem of Calculus, Part 2, tells us that, tells us this: the definite integral of any continuous function can be calculated without taking limits or calculating Riemann sums. So that's what I was talking about earlier. We don't have to approximate anymore with Riemann sums, or think about what happens with the limit as all those rectangles approach infinity. We can just do this process, and we're going to know the area under the curve, the integral. We're going to be able to figure out, we're going to be able to evaluate the integral, as long as an antiderivative can be found. All right. So if it's possible, we're going to be able to do it. So here we go. Let's so get that down. That's in words what we're going to do. So here it is. Let's look at these 2 examples. So this is the first one. This is a pretty simple example, but again, I'm just trying to show you the process here. Now, guys, we're going to talk about we're going to get into different types of functions, guys. But for right now, let's just settle on polynomial functions, okay? Things that we know forward and backwards here. So if we want to evaluate the integral from -1 to 3 of x cubed plus 1 dx. All right, let's see what we can do here. Well, first of all, let me go back here and say, this is how you do this. All right, in order to find this is what we have right now. We need to take capital F of b minus capital F of a. And just to review again, capital F means find the antiderivative. So, with a polynomial function, how do we find antiderivatives? Well, let's start with the first term. So what would we do to find the antiderivative of x cubed? So what that means is, what term originally, or what function originally, if I took the derivative of that function, I would get x cubed. All right, so the way to do this, remember with differentiation, we would subtract 1 from the exponent, and then we would multiply, we would multiply by the exponent and then subtract 1 from it. Okay? Well, the opposite of that is going to be the antiderivative. So we're going to divide, we're going to add 1 to the new exponent. We're going to add 1 to the exponent, and then we're going to divide by the new exponent. So guys, the antiderivative of x cubed is going to be add 1 to the exponent, x to the 4th, over, and then we have to divide by the new exponent. So it's x to the 4th over 4. Okay, so that's the first thing. That's the first term we've evaluated. We've taken the antiderivative of. Now let's do the second one. Now, off to the side here, I just want to mention this, and guys, you probably already know this, what the antiderivative of 1 is, but just to be thorough here, 1 is the same thing as 1x to the 0 power, isn't it? Because what is x to the 0 power? The answer is 1. Okay, so let's evaluate this. So let's do the same exact thing. So if we add 1 to the exponent here, we're going to get 1x to the 1st, and then we're going to divide by the new exponent, which is 1. Well, x to the 1st over 1 is x. So guys, this guy if we take the antiderivative of 1, it gives us x. Okay, let me get rid of that stuff. That was off to the side information. All right, now, this is where, you can write this different ways from here on out. This is the way I write it. I still need to say I need to evaluate that over the interval from -1 to 3. Okay? So the way I usually do this is to remind myself, I put a little bar over here, put the lower limit of integration there, the upper limit here, to say I still need to evaluate that. All right, I haven't done much. The only thing I've done is find the antiderivative of the function. So now we actually have to apply the second part of the fundamental theorem of calculus. We've got to do this. All right, so we've got to take capital F of b, which means the antiderivative evaluated at b minus the antiderivative evaluated at a. So let me ask you, Corbin, either Corbin, which one of these is b? Yep. Well, hopefully you got it right. 3 is b. Okay. That is going to be our upper limit. A is our lower limit of integration. So we got to take f of b minus f of a. So what that means is f of, we said b was 3, minus f of a is going to be, process of elimination, -1. Okay. Let's keep it going. Okay, so guys, all this means is I need to plug this into my antiderivative. I need to plug 3 in. So let's do that. I'm going to write it all down, show all my steps here. I'm not going to do any work in my head, really, yet. So it's going to be, we got to plug in 3. So it's going to be 3 to the 4th over 4 plus 3. Let me write it down. That's what f of 3 is going to be. F of -1, we still have to put this minus here. This is what throws a lot of people off, guys. That is a minus. Put whatever you have over here in parentheses. A lot of people don't do that, and that'll mess your answer up. So let's plug in a -1. So it's going to be -1 to the 4th over 4 plus -1. So I'm doing the same thing. I'm plugging both of those back into the antiderivative, and watch what that's going to watch what's going to happen here. We got 3 to the 4th, which, if you type that in your calculator, is going to be 81, plus 3, minus, -1 to the 4th is positive 1/4. Whoops, fix that. We still have this -1. Now what I would do, I would just leave it as fractions, guys. How do we add fractions? Well, we got to get the same denominator. So this one's over 4. It would be nice if we could put that over 4. So 3 is the same thing as, that's right, 12 over 4. And let's do the same thing over here. We got 1/4 minus, 1's the same thing as 4 over 4, so it's minus 4 over 4. Okay, I let's just go ahead and add these. So 81 plus 12, 93. 93 over 4 minus 1/4 minus 4/4 is negative 3/4. So when we minus a negative, it gives us a positive. So we're going to add those. And so that'll give us 96 over 4. Guys, type that in your calculator. 96 divided by 4 is going to be 24. So the area under the curve of this function from -1 to 3 is going to be 24. Now, I wasn't planning on doing this, but probably a good idea to show you guys to make a connection here between this and the Riemann sums. So let me just do this real quick and bring this up. I'm hoping the video is going to pick this up as well. Let's see what I want to do. Oh yeah, Riemann sums interactive. Okay, so we've been here many times before. I've showed you this. Let me type in my function. It was x cubed. What was it, +1, I think? Let me just double check that real quick. I don't want to mess this up. Yeah, x cubed +1. Gonna hit enter. There's my function. Now we wanted it to go from -1 to 3. Look at that, I got the sliders right. From -1 to 3. And doesn't matter which sum we use. Let's go to the midpoint sums. Usually that's the more precise one. Well, let me let it go to 100. So essentially we're going to try to find the area of this rectangle. So I don't know if you guys can see this on the video. But right now at 42 rectangles, the area was 23.99. And as I go further at 100, hopefully you can see this, it says the area is 24. Alright, so it's already rounded it. So that right there, with 100 rectangles, that was a pretty close approximation. It's probably 23.99999, but eventually it rounds it up to 24. But yeah, we can see that we got it right. The area under the curve is going to be 24. Okay? So hopefully that makes sense. Let's keep it going. Alright, so that's a little bit of a review of the Riemann sums stuff that we worked on at the beginning of this section. This chapter, I should say. Alright, last one. This will be the last example I get to in this video. Let's talk about this right here. So we're going to find the area of the region between the curve y equals 4 minus x squared, the interval from 0 to 3, okay, we want x to be between 0 and 3, and the x-axis. I want you guys to notice how that's worded. Okay, notice what the question's asking. That's always important. Obviously, we want to try to answer the question. So, get this down. I'm going to go back here real quick. Notice the difference between the wording of this and the wording of that. Okay? So guys, I want you to think about this. We talked about this in a previous section. I think it was in 5.2. What the integral means. Okay? Now if you remember, the integral means the net area. Okay? So what it means is you take the area under the curve that's positive and you subtract the area under the curve that's negative. Okay? That gives the net area under the curve. Well guys, if it reads like this, it doesn't tell us the net area. We want to find the actual area between the curve and the x-axis in this interval from 0 to 3. So let me graph this and let me show you how this looks graphically, and I'll explain this a little bit further. So here it goes. I'm going to draw this in green. We know what 4 minus x squared should look like, hopefully. It's going to be a parabola. It's going to be a parabola opening down, and its vertex is going to be right here at 4. So I'm only going to graph it from 0 to 3. Zero, 3. Now, I know 3 is going to be out here before I even graph it because I could figure that out by finding my 0. If I found that wherever it crosses the x-axis, let me do that real quick. So guys, in order to find the x-intercept, we let y equal 0. Okay. So 0 is going to equal 4 minus x squared, and then just to solve here, I would get x squared is equal to 4. Square root both sides. So x is going to be plus or minus 2. So yeah, the other, if I were to draw this side here, this would be negative 2. This would be positive 2. So that's how I knew 3 was to the right of my 0. Okay. So guys, we are trying to find the area between that curve and the x-axis. So let me draw what we're trying to find. We're trying to find that area, and we're trying to find this area. Now, we want to find both of those areas, but area in general, we want these to both be positive, okay? That's what this means. And when it says find the area between the region, the area of the region between the curve and the x-axis, we need to add this area to this area. Now, if we just go ahead and integrate from 0 to 3, it's going to take this area and subtract this area. So I want to make sure you guys are aware of that, okay? So we can't just take the integral from 0 to 3. So what I want you to do is think about, well, how could we do this? How could we figure out the area between the area between the curve and the x-axis? Think about it a little bit. Anybody can answer at any time. I'm going to pretend like you guys said the right answer. We could divide this into subintervals. So I could find the area under the curve from 0 to 2, and then I could find the area of the curve from 2 to 3. All right, and then take the guys, if I find the area under the curve from 2 to 3, it's probably going to give me a negative area, and I'll have to take the absolute value of it. Okay? So if it gives me, I'm just making up a number here. So if it gives me that this area is 4, negative 4, I should say, then the actual area is going to be 4. Does that make sense? All right? So it should give us a negative area here. We're going to make it positive if we want to talk about the area between the curve and the x-axis. So here we go. Let's do this. So again, what I'm going to try to do is I'm going to take the integral from 0 to 2 of my function, which is 4 minus x squared dx. And then I'm going to add that. And by the way, I'm going to take the absolute value of this plus the absolute value of the integral from 2 to 3, 4 minus x squared dx. Now, you probably don't need to write the absolute value here because if you look at the graph, you know it's going to give you a positive area right there from 0 to 2. So we don't even really need to worry about that absolute value. But we will have to take the absolute value of this area from 2 to 3 because it's going to be below the x-axis. Okay, so let's go and get rolling here. So we just did an example where we figured out how to do this, how to evaluate this from 0 to 2. And what do we have to find first? And if you said find the antiderivative, you're the winner. Okay, tell them what they've won. Pride. So let's keep going. I'm going to add, so when you find the antiderivative, you need to add 1 to the exponent and then divide by the new exponent. So what's the antiderivative of 4? Yeah, that's right, 4x. What is the antiderivative of negative x squared? Good, negative x cubed over 3. Okay, add 1 to the exponent, divide by the new exponent. And then we're going to evaluate that from 0 to 2. Okay. And over here. Well guys, good thing about this, I already took the antiderivative, so I know what it is. It's going to be 4x minus x cubed over 3. But we're going to evaluate that from 2 to 3. Now I'm going to get rid of my absolute values for right now. Guys, just know I'm going to come back and I'm going to find the absolute value of this eventually. Alright, we'll come back to it. So here we go, let's keep going. So, in order to evaluate this from 0 to 2, again, the formula is capital F of B minus capital F of A. So what is little b? Little b is going to be 2. Just disregard that. Capital F of A, little a is going to be 0. Okay? 0 is our lower interval, lower limit. 2 is our upper limit of integration. Okay. So here we go. Let's start plugging this stuff in. I was trying to determine, do I want to do this in my head? It might confuse you if I do, so let me write all this out. Here we go. I'm going to do it in blue. So f of 2 is going to end up being 4 times 2 minus 2 cubed over 3. So that's just that part of it. Then we're going to subtract f of 0, How about I do that in my head? 4 times 0 is 0, minus 0 cubed over 3. That's 0. 0 minus 0, 0. So that's nice. That helps us out. And then we're going to add, well, it's still going to be, let me do some green stuff. So it's still going to be f of b minus f of a. But my b and a have changed here. So it's going to be f of 3 in this case, minus f of 2. Okay. Keep it going. Let me write out f of 3. So f of 3, plus here, blue. So f of 3 is 4 times 3 minus, what is it, 3 cubed over 3, I think. Let me go back up to make sure. Yep. And then we're still going to have this minus 4 times 2. Minus 2 cubed over 3. Okay, we just got to do some arithmetic, guys. Let's just do it one step at a time. So this is 8 minus, this will be 8 thirds. The 0 doesn't really matter. This will be 12 minus, guys, 3 cubed is 27. 27 divided by 3 is 9. Minus 4 times 2 is 8. This is 8 thirds again. So if you wanted to, you could have simplified this. Whatever we get here is exactly the same as what we get here. All right, so let's keep it rolling. Just keep simplifying, guys. 8 is the same thing as 24 thirds. I'll go ahead and subtract those. That's 3, and then minus 24 thirds. Why don't we do this? Hey, 24 thirds over here, negative 24 thirds over there. How about we cancel those? 3 is the same thing as, son of a gun. No. My bad. Don't do that. Don't do that. That's my fault. I'm messing stuff up here. That's my bad. Guys, I just want to, okay, so let me rewind here. This right over here, let me break these apart. I'm going to cut these in half here. This right here is f of 2 minus f of 0. Alright, so let's do that first and figure out what that is. Let's keep these separate, okay, because 3 minus 24 over 3, that is this, f of 3 minus f of 2. Okay, so let's figure that out first, then we'll have to take the absolute value of it, alright, and then let's add them. Okay, hopefully that made sense. So me getting rid of the absolute values really messed me up. I should have kept them in here. So let me go back and do that. So hopefully this makes sense. So we want to find the, let me do this in red, the absolute value of this side. So let's keep the absolute value. We're going to keep the absolute values here. Okay, so now we're good to go. I know things are getting cluttered here, guys. I apologize for that. So yes, we can go ahead and do this. This is going to be 16 over 3 is what that guy's going to be. Now this one over here, this is going to end up being 9 thirds minus 24 thirds. Shoot. Sorry, we're still good. We're still good. I just can't think of how to do this. I'm drawing a blank. I think 9 minus 24, yeah, negative 15. That's my bad. It's negative 15. We're still doing absolute values of that. So negative 15 thirds. Well, what's negative 15 thirds? Sorry, I could have, my bad. I could have saved a lot of time here. 9 thirds is 3. 24 thirds is, that's 8, isn't it? So 3 minus 8, that's negative 5. Well, okay, might as well write it as negative 15 thirds. Negative 15 thirds, same thing as negative 9 thirds. I'm sorry, guys. Wow, that's bad. Okay, negative 15 thirds, same thing as negative 5. Okay. I know you guys are thoroughly confused by now, but I apologize. Again, I'm sorry. So, what's the absolute value of negative 15 thirds? Positive 15 thirds. So we have 16 thirds plus 15 thirds. The answer is 31 thirds. I'm hoping that's the right answer. Where did I mess up? Daggone it. Messed up somewhere. That's not the answer. You guys have probably been yelling at me the whole time. I'm going to pause this right here. The next video will have the answer to what I missed.